This video is a product tutorial that covers moving from the ASH WARE simulation environment to the target hardware environment in which a host CPU controls a MC33816 across a SPI bus. There are also start signals that provide precise injection timing. However, these are not the topic of this tutorial, so will not be discussed further. Before moving to the CPU MC33816 co-simulation, let's take a brief look at three key files in the standard MC33816 standalone simulation environment. The first file is the source code file. The source code file contains numerous opcodes here, here, and here. At the top of the source code file are variables. These variables get initialized. For instance, variable iBoost gets initialized with a value of 255. If no initialization value is in the code, a 0 is used. The second file is the startup script commands file. This is a really key file, so pay close attention. There are a lot of registers. Let's look at a feedback sensitivity register at address 180. Hover the mouse over the macro name to get general information. Hover over an argument to get more detailed information about that argument. Double-click on an argument to change it and get information on what each of the argument values means. Notice that the file consists of a large number of these _WR macros. Each of these represents a SPI write. In the simulation environment, this startup script provides boot up initialization by automatically executing all at once every time you reset the simulator. The last file is the primary script commands file. It consists of a series of script commands. This script command writes the MC33816's flash enable register, which causes the MC33816's core to begin executing code. This script command wiggles the drive enable pin. Timing script commands such as wait time control when these script commands execute. Okay, that is it for the standalone simulation environment. Let's move to the target hardware environment, which is mimicked in the CPU MC33816 co-simulation environment. The MC33816 is controlled and monitored via the SPI bus by code running in the host CPU. Let's look at how the three key simulator files, the source code file, the startup script commands file, and the primary script commands file, are used within the host CPU source code. The startup script commands file contains a series of register initializations. The startup script is included into the source code using a #include. These are organized into 5 contiguous blocks held in 5 int16 data arrays named channel1_config, channel2_config, diag_config, io_config, and main_config. Each of these is transferred as a SPI block write from the host CPU to the MC33816. We'll look at the source code that does this in a bit. Variable initialization. In the MC33816 source code, variables either are assigned initial values or are initialized to 0. The assembler produces 2 auto-generated files that end in data_ram.c and .h that contain these initial values. These 2 files are included into the startup script, which are in turn included into the host CPU's source code, as we saw before. These files go into the array named channel1_data_ram, which the host CPU writes to the MC33816 in another SPI block write. If the second MC33816 channel were used in this demo, there would be a second int16 data array and SPI block write. Next are the opcodes from the MC33816 source code. The assembler generates another 2 auto-generated files ending in code_ram.h and .c. These are included into the source code file to form another int16 data array named channel1_code_ram, and similar to the data initialization, were this demo to use the second MC33816 channel, there would be another int16 data array and SPY block write for that second channel. The last key MC33816 file from the standalone simulation environment is the primary script commands file, which, as you will recall, does sequence writes and reads to and from the MC33816. In this demo, we are not making use of this file. However, it is possible to export this file using the script command create SPY commands file, which creates a .spy file. This too could be included into the host CPU source code to generate a series of SPY word writes and SPY word reads. In fact, this is the method we use to conformance test our MC33816 simulated model against the actual MC33816 hardware. Let's open the CPU MC33816 demo, in which the code running in the host CPU controls the MC33816 using a series of SPY writes. From the Windows Start menu, select the Direct Injection Moving to Hardware demo. Note that in this demo, there's a simulated CPU here and a simulated MC33816 here. Finally, let's step the simulation through the portion of the host CPU's code that initializes the MC33816 to see how it all plays together. Reset the simulator. Single step until the load MC33816 data RAM function gets called. Step into the call. Here we have function write SPY words, which in your target hardware's host CPU is a single fast SPY block write. Up here I see the same function called to perform the SPY block write of the code image. And down here another function does some more block copies of the 5 MC33816 register blocks. Stepping further, we get to the point in the code where a single SPY word write enables the channel that will generate the injection pulses. And from here to here is a forever loop that generates the rather coarse start signals. However, this part of the code is likely not applicable, as you'll probably want to generate more precise start signals using a precision timer such as the Freescale eTPU. However, it is fun to step through the loop and watch the pretty simulation. Popcorn, anyone? That is it for this demo. Thank you for watching. Note that we have additional videos that cover specific product features in greater detail on our website at ashware.com/product_videos.htm. There are also videos that cover our other demos at the same location. ASH WARE, development tools since 1994.